Alright, so let's do the helper number 4. The set of problem that I want you to actually work on is these guys. So let's do the question 1. So the frequency is 10 megahertz, and then the wavelength is 1 centimeter. What is the speed? So the wave is always look like this, right? And then the wavelength is peak to peak, and that one right there is 1 centimeter, right? Or 0.01 meter. I like to use SI unit, so I'm going to stick with that one. And then this wave, the one complete period, is going to repeat 10 times 10 to the 6 hertz. That means times every second. So that just means that it's hertz, okay? In the unit it looks like this. So if the peak to peak is 0.01, the period, not period, sorry, the wavelength is 0.01 meters, and then it's going to repeat that many times, then the distance covered by this wave every second is simply multiplication of these two numbers, right? So that's equal to 0.1 times 10 to the 6 meter every second. So that's the speed. You can actually change this one to the 10 to the 5 meters per second if you want to, but it's the same stuff. So basically that you find the unit length, which is the unit length of the wavelength, and then how many times does it repeat every second, and multiply that, you get the distance that's covered by usually second. Then distance divided by time is the speed, so automatically that answer is going to be speed in meter per second. Alright, that's good enough. So let's do the question number 2. Alright, if the light is 100 nanometer, what is its energies? We are talking about light, right? So we can always use this relationship. I don't have the frequency, but I do have the wavelength, right? So I can actually rearrange this formula and then plug these things, the whole thing, into here. Alright, that's more like what I want to use. So h is 6.6 times 10 to the negative 34. C is the speed of light, 3 times 10 to the 8. And then wavelength is 100 times 10 to the negative 9, right? So let's just put all these numbers into the Excel. Equal 6.6 e to the negative 34 times 3e8, the speed of light, divided by 100 e to the negative 9. So that's energy of the light. Notice that I changed everything to the SI unit, so what comes out of the equation is always SI unit, so I automatically get the joule. Alright, let's do the next problem. So if 1 gram of water requires 4 joule of energy to 4 joule to raise the temperature by 1 degree Celsius. Then how much energy is required to raise a cup of water, which is 250 grams, by 20 degrees? So in another words, I have 1 gram of water, 250 units of those, and then I'm going to raise the temperature 1 degree per step 20 times. I need to change that one a little bit. So 1 gram of water, 250 of those, and then I'm gonna need 4.184 joule to raise the temperature by 1 degree Celsius, right? And then I do that for 20 times. So that's the stuff I need. So 1 equal 1 times 250 times 4.1 multiplied by 20. So that's the energy I need to raise the temperature of the cup of water by 20 degrees Celsius. Alright, that's good enough. Next is that energy is equivalent to how many photons. So the energy required to raise the cup of water temperature by 20 degrees, 920, right? And that energy is equivalent to how many of those things combined together. So the question is just what do you get if you divide 2920 divided by each photon energies, and that many photons are required. Alright, that's good. Okay, let's do the next problem. What is the wavelength of the proton? Now, this time around it's not light, so I cannot use this formula anymore. Okay, that thing is gone. Proton is what's in the nucleus, right? So we know the mass, and then we know the speed for these things, right? That's given information. So the stuff that we can actually use is de Broglie's relations. So wavelength is equal to Planck constant divided by momentum. The momentum is mass times speed, right? So that's pretty much all we need. Alright, so let me just try to erase the one in the middle. That's the formula, right? So h is 6.6 times 10 to the negative 34 as usual, and then velocity is 200k, and then mass of proton is 1 gram per every mole, right? I may be wrong on this one, but the Avogadro numbers here. Then 1 gram is 0.001 kilogram. I need to use SI unit, right? And that number right here is gonna go in here, and that should give me the wavelengths. So let's do that one. So it's equal to 6.6 e to the negative 34 divided by, always use a parenthesis, 0.001 divided by 6.022. I think this sounds better. Multiply by 200k. Alright, so So that is the wavelengths in meter. Because I'm using the SI unit for each one of those, I always get the SI unit output. So that's the answer to this question. Okay, let's do the next problem. If the uncertainty of the momentum is this, what is the uncertainty of the positions? So the formula that we are going to use is the Heisenberg uncertainty principle, which is always bigger than this number right here. The pi is 3.14, and then h is 6.6 times 10 to the negative 34. So the p right here, uncertainty in momentum is this one. We look like we can actually plug in this number into here, right? Because it's SI unit or SI unit, right? So we should get the meter in this one by just plugging all of these things. Now the key to actually solve the uncertainty problem is to replace this inequality with the equal sign. Always. The reason why I say that is because what you're looking for is minimum uncertainties, right? Because this problem is always satisfied by actually putting the absurdly the big numbers close to infinities, right? And nobody's interested in that. So what we want is a minimum uncertainties. For that, we just need to replace all of those inequality to the equal sign. And once we actually do that, then this problem is fairly simple. Just solve for these equations, because we know the delta p, we know h, we know 4, we know pi, then we can solve for this uncertainties in positions. So equal 6.6 e to the negative 34 divided by 4 times 3.14159, divide both sides by 10,000. Alright, so that's the uncertainty of the position in meter. And I think that's good enough to actually prep for the in-class quiz number 4.